Hi everybody, welcome to our first video on related rates in Chapter 4. Just an FYI, this will be the first video in a three-part series which will equate or relate to the three examples in the notes packet. So we're going to start first with example 1 in related rates. And the first example is probably going to be the longest because I have to talk about a lot of new things. So let me start by just reading the problem. It says, a 20-foot ladder is leaning against a wall. If the bottom of the ladder is pulled along the level pavement directly away from the wall at a rate of 2 feet per second, how fast is the top of the ladder moving down the wall at the instant the foot of the ladder is 4 feet from the wall? Okay, so you see I have a little template set up here. And this template can actually be used for any related rate problem that we do, so feel free to use it. The first thing I always do is I draw a diagram. This will be pretty easy. So we've got a wall that meets the ground at a 90-degree angle. And we've got a 20-foot ladder leaning up against this wall. So this is the wall, the ground, or the pavement, they said. And I'll just put in here, I'm no artist, so forgive me. Here's my 20-foot ladder. And I'm going to go ahead and put 20 feet on there because this dimension is fixed. That ladder is going to remain 20 feet no matter what else is going on here. That's fixed and unchanging. And in related rate problems, when you have unchanging values, you can feel free to put them right on your diagram. Now, there are a couple things that are changing. For instance, when the base of the ladder is pulled directly away from the wall, which is what they told me was happening, the length that is now between the wall and the base of the ladder, I'm going to call that length X, that's changing. As we pull this outward from the wall, X is going to change. So that's why I'm giving it a variable, because it's going to be a changing value. Similarly, as we do that, we're going to assume that the top of the ladder stays in contact with the wall and kind of glides down the wall. As this gets pulled out, this is going to kind of scoot down the wall. Excuse me. So I'm going to call the distance between the ground and the top of the ladder, I'm going to go ahead and call that Y. Again, it's a changing value as we move the ladder, so we'll call that Y. And that's about all I can really put on my diagram. So now I'm going to move into my given information. Okay, well the 20-foot ladder, I've already kind of taken care of that. The next sentence says that the bottom of the ladder is pulled away at a rate of 2 feet per second. Okay, so X is changing at a rate of 2 feet per second. What I like to do is I'll put the 2 feet per second down, which helps me with my label. This is actually the change in X, which I'll call dx, with respect to time. The seconds goes with the time, and the feet goes with the X value because X is measured in feet. So dx dt is equal to 2 feet per second. Okay. What else do I know? If I keep reading, how fast is the top of the ladder moving down the wall? Okay, that information, I'm actually going to put that in the trying to find section. That'll be what I'm trying to find. How fast is the top of the ladder moving down the wall? So I'll be looking for how quickly this is changing here. So I'll be looking for the change in Y with respect to time. I don't know what that is, so I will put a question mark. But I do know my units. Y is going to be measured in feet, and time in seconds. Okay, let me keep reading. How fast is the top of the ladder moving down the wall? At the instant, the foot of the ladder is 4 feet from the wall. So at the instant, this distance right here, X, is 4. So at the instant, x is 4 feet. Okay, so I've got my givens, and I've got what I'm trying to find. The next part of this problem is that I need to write an equation that involves the variable I'm trying to find and my givens and the diagram. So if I look at this, the first equation that's going to come to my mind that's going to relate this diagram with x's and y's is the Pythagorean theorem. So my equation is going to be x squared plus y squared equals the latter 20 squared. And if I square out that 20, I'm going to have x squared plus y squared equals 400. Okay, now that's a great equation. The problem with this equation is it doesn't have anything to do with time. And all of what I'm looking for, what I'm given here, has feet per second. So how the heck am I going to bring seconds into this Pythagorean theorem, which only involves distances at this point? Well, there is a way, and it's going to occur in my section called differentiation. I am going to implicitly, and you remember that from chapter 3, I can force any variable into a problem if I implicitly differentiate with respect to the item I want to force in here. In this case, it's time, or t. And I'm going to show you how that works. So what I'm going to do is recopy my Pythagorean theorem over here. X squared plus y squared equals 400. Now, in order to implicitly differentiate, you know you do not have to solve for any particular variable. You can just leave your equation as is, which is nice. And what I'm going to do in front of each term is I'm going to take the derivative of each term with respect to time. This is how I force it in. So the derivative with respect to time of x squared plus the derivative with respect to time of y squared is going to equal the derivative with respect to time of 400. All right? Now, one of these is easy to do. I can find the derivative with respect to time of 400 because it's a constant. So that's just going to be 0. But the other two are not so straightforward. I cannot differentiate x squared with respect to t. I just can't, because this is not a t. So if you remember from chapter 3 when we first learned implicit differentiation, you kind of finagle this and you write it like this. The derivative with respect to x of x squared, because that I can do. But then you got to tack on dx dt so that the problem doesn't change. If you look at this and you look at what you started with, nothing's changed. If you cancel out these dx's, you're left with d over dt of x squared, d over dt of x squared. So what ends up happening here, the derivative of x squared with respect to x is 2x, tack on dx dt. So I'm going to actually let you do that moving forward. I'm not going to make you show this step and this step with each related rate problem, but I do want you to realize this is the reason I'm going to say that when you differentiate x squared with respect to time, the answer is 2x, go ahead and differentiate it, but tack on whatever variable this is, in this case x, dx dt. Let's look at how that works with the next term. You cannot take the derivative of y squared with respect to the variable t. So we'll switch it to the derivative with respect to y of y squared and tack on dy dt, because now we have the same problem. The dy's would cancel, and we would just have d over dt of y squared. But when it's written like this, I can actually do it. So the derivative of y squared with respect to y is 2y, tack on dy dt, and this is all equal to 0. So once again, I'm going to let you go from this step straight to this step. Differentiate dx dt, differentiate dy dt, and then 0. But this is the reason why. Okay, very good. My next step says, fill in and solve. Okay, so this is interesting. For this step, we have to go back to what we're trying to find. We are trying to find dy dt. So where is that over here? Okay, so this is what we're trying to find. So let's fill in everything else that we can from the givens and see if we can then solve for what we're trying to find. So let's see, working from left to right, we have a 2x. Well, x is 4 from the givens, so 2 times 4 times, we were given dx dt. What was that? 2 feet per second. So 2 times 4 times 2 plus 2y. Okay, did they give me a y? They did not give me a y. But it is simple to find if you just do a little side work here. Sometimes you're required to go back and get things pretty easily that you need. We can find y at the moment x is 4 by plugging in 4 and 20 into the Pythagorean theorem and solving for y. So my side work would look like this. Here's my diagram again. We know we have the 20-foot ladder. We're looking for y. At the moment, x is 4. At the moment, the base of the ladder, I said 4 and wrote an x. This is 4. So if I just quickly run a Pythagorean theorem, I would have 4 squared plus y squared equals 20 squared. And that would give me 16 plus y squared equals 400. If I subtract 16 from both sides, I get y squared equals 384. And if I square root, y would equal plus or minus the square root of 384, but that wouldn't make sense since y is a distance here. Negative wouldn't make sense, so I'm just going to go ahead and say y is the positive square root of 384. So this is what I'm going to fill in here for my y. So now I have 2 times the square root of 384 times dy dt equals 0. So this is just this guy copied over with things filled in. And if you notice, the only thing that's not filled in is dy dt, and that's what I want to find. So using a little algebra, I'm going to solve for that. So 2 times 4 times 2, of course, is 16, plus 2 square root 384 dy dt equals 0. Solving for dy dt, I'm going to subtract 16 from both sides. So I have 2 square root 384 dy dt equals negative 16. And my final step will just be to divide both sides by 2 times the square root of 384. Cross those out. So dy dt equals, and then I will appeal to my TI-84. Now throw this under here. If I like to do alpha y equals, choose number 1. If you don't have that option, you'll just have to divide. Negative 16 on the top, and 2 square root 384 on the bottom, and that gives me negative 0.408, and we are going to round 1,000, so negative 0.408, and then I go back to what my units were, feet per second. Now let's talk a little bit about that. The reason that the change in y comes out to be negative is because if you look at the diagram and think about this, the distance between the ladder, the top of the ladder, and the ground, that is going to be decreasing. So we talked in Chapter 3 about velocity being positive or negative, and the reason for that is that the velocity will show direction, positive up, negative down, positive increasing, negative decreasing. So it makes sense that the change is negative. Now, when I make my final statement, which I'm going to reveal here, you'll see I get rid of the negative, and there's a reason for that because I use the word down, and it's implied. So here's my final statement. When the foot of the ladder is 4 feet from the wall, the top of the ladder is moving, here it is, down the wall at a rate of 0.408 feet each second. Because I use the word down, I may take the negative off. If I was just saying, hey, the distance between the top of the ladder and the wall is changing at a rate of, and I didn't use the direction, then I would have to keep the negative. But because the direction is implied here, the negative is implied. Feel free to pause this so that you can copy that statement down, and the next video will take us into example 2.